This is part two now. So we've talked about constraints and we've talked about some cascade and update on delete and things like that. We talked about some triggers. Now I want to talk about some database performance issues. So there's different factors that you're going to affect when you create your database as far as the performance of the database. You need to take all of these into consideration when you're creating your database. And again, it depends on how you're using this database as to whether it's a transactional based database. So what I mean by that is that you're doing you're inputting a lot of records. So it's a maybe a POS for a store or something like that. That's a transactional based database, as opposed to a reporting database. So it's the same data maybe as the POS, but it's the one that my corporate headquarters is using to make some strategic decisions for the company. So there's two different kinds of databases that we're talking about there. So you can have large amounts of data that are going to affect how big each record is, and affect how much time it takes to query the database. You have different structures that that help determine the performance. So you can have your keys, your primary or your composite key. So is your primary key a single key or a composite? And then we'll talk about some indexes as well. Different data storage factors. So do you want to have your data split into multiple disks so that you can have faster accesses for multiple people or not? Your need for your joins. So joins are an expensive operation and there's just no way around them. But if you're using this database for a querying, reporting kind of purpose, you're not doing updates on it, it may make sense for you to denormalize that database so that you have fewer joins. And then you have some business environment factors. How often are certain tables accessed? Maybe you have some tables that are rarely accessed, and you can treat those differently than the ones that are accessed frequently. So there's two different approaches here. You can either change your logical design or you cannot change your logical design. You can see them on the left and the right. So for your design techniques, if you're not going to change your logical design, you've already got that, you're happy with that, then you need to, if you're going to tune the database for performance, you can add indexes, you can add views, and we'll talk about what a view is as well. And then what you can also do is you can partition your database. You can partition it horizontally or vertically, and I got a slide on that too, so we'll talk about that. If I need to, or if I want to, I can change my logical design. So what I can do is I can add new primary keys. So if I had a primary key that was 4 or 5 different columns, it's going to make better sense for you to have a primary key of a single column that you've generated to avoid all of that. You can also combine tables. That's like I talked about denormalizing your database. So all of those one-to-one relationships, maybe you combine those into a table so that you get rid of those some of your joins. Oops. So that you have these features in the database called an index, and it's not it's part of the database design, but it's not part of your data. So it's stored separately. But what it is it's a mechanism that allows you to go in and directly access some specific data that you've asked for. So if you think of an index, it's similar to the telephone book, which I know nobody uses. But if you look in your telephone book, everything is alphabetical, and then there's little black, usually little black colors on the outside. Black colors. Well, that was anyway. Little black tabs on the outside. So that you can see where the A's and the B's and the C's are. So an index is similar to that. You can figure out really quickly where to look in the phone book for, who was that? Some Alice Beaton or whoever her name was. So you could go and find that name in the phone book. An index allows you to do the same thing. It allows you to quickly find a particular row or rows of data that you want. you can get an index on a primary key, and the database, I don't know of a database that doesn't do that by default, so, but there may be, but that's usually the default. The database creates an index on the columns that you've created as the primary keys. But you can also create an index on the foreign keys, or if any kind of column that you do a frequent search on. So maybe you're going to do a search on last names or regions within a sales company or something like that. You can put indexes on these other attributes. You can create too many indexes because they take resources to update. So you want to make sure you don't have too many. You only want the ones that you need. And it is possible to have more indexes than tables, and so your indexes take up more space. If you have a small table, that it may not be necessary to create an index for it if it's a small table. Let's say it's the states table. You have a list of all of the states and the abbreviation that goes along with that state. That's 50 rows plus territories and that kind of stuff. So it's not a very big table, and the database can read that into memory rather quickly. So you wouldn't need an index for that. Now, if you're working without indexes, which is possible, when you query your table and you're going to find a particular piece of data that you need, what happens is that the database is going to perform a table scan. So if you can think about, I have 1,000,000 rows of data in my database, and they're my customers, let's say. And I'm going to go and I'm searching for customer ABC. Then that index or that table scan is going to have to go through every row one at a time until it finds company ABC. And if it's alphabetical by coincidence, then I guess that's not bad, but what if it's customer ZXY? Then it's going to have to scan all 1,000,000 rows to find that one customer. And then what it's going to do is it's going to return that one row that meets your condition. So that takes a long time in doing a query. In doing any kind of updates, if you're adding a row or inserting a row, you're updating or deleting a row, without indexes, all you do is affect that one row. There's nothing else. There's no other data structure out there to worry about. So that makes those a little fast. Without the indexes, you're going to have slower queries, and you're going to have more disk accesses. And the reason you have the more disk accesses is that it has to do that table scan. So that disk access is going to, the head is going to move around on the disk to find wherever that segment is, and it's going to have to get that piece of data and look at it to make sure it's what you've asked for, and if it's not, it's going to have to keep doing that over and over and over again. But it is going to be faster maintenance because I don't have to update my indices like I do if I'm using them. So here's an example of a bunch of tables. The indices, however you want to say it, in the red are the ones that the DBMS creates for us because those are the primary keys. So like I said before, the database or the DBMS is going to create indices for you based on your primary keys. The let's see, H, I, and G, those indexes are going to have to be created by you as the database administrator. And that what it's saying is that the salesperson table, we're going to search a lot on that table for salesperson name. And on the customer table, I want to be able to search by salesperson number to find excuse me, all the customers. And then this last one, sales. I want to be able to search on just the product number. It's not the primary key, salesperson number, product number. It's just product number. So I would have to create those indices on my own. If I'm using an index within my database, now the last example we were not, and so I was explaining the differences there. Here we're using an index. So what happens is that the index is going to be read into memory. So if I have 1,000,000 rows, it's going to read however that index is stored, and there's different ways to to have indexes, so that's going to be read into memory. So the database can then, or the DBMS uses that index, and it can search through the index to find out where that record is located, and then just go out and directly access that record. As far as if I'm doing any kind of updating, if I'm inserting, updating, or deleting a record, it not only has to affect that record with the insert, update, delete, but it also has to update the index that's there. So if I have a table that has, I don't know, 3 or 4 indexes on the table, and I insert a new row, it has to also update those 3 or 4 indexes. So that's going to take a little bit of time. So that's where the trade-offs are. Your queries are going to be faster because I don't have as many disk accesses. I can just go straight to where it is. But my maintenance is going to be slower because I'm going to have to go out and write for my index as well as the row that I'm affecting. And if I'm doing just a query database, that's what it means here by static database. The database isn't changing. It's a reporting database. Then I'm going to gain by having the indexes there because my queries are going to go much faster. If it's a transactional-based database, then it's going to go much slower because, well, not much slower. It's going to go slower because I have to not only affect the row, but I have to affect the index that I'm updating as well. And not that that's a bad thing. If it's you're doing updates on an employee table, maybe it makes sense to have an index based on last name so you can just go through and search on that. And it's okay to take the hit on updating an index every time you insert a new employee. It's one index. It's not that big a deal, but it's going to give you better performance on your actual application, because when somebody goes to search for all of the or a particular employee based on last name, then they're going to be able to find them that much faster. So this is one way of implementing an index. It's called a B+ tree. And these are the IDs, or these are the primary keys for whatever table this is indexing. So you're going to pick whatever. Oh, I thought I had it before that. So that's an example, or I can have it in ranges as well. You can see I have ranges here. So if I want to look up number 130, it starts at the top of the tree, and it sees that the number is 90. Is 130 greater or less than? So it's greater, so it's going to go to the right, and you can see that. And then it finds this next node, and it's got 105 and 135. Well, 130 is in between those, so it's going to go and take that route. And then it's going to find 130 right there. Well, I need to move my circle. And then it'll be able to access that row. And you can see it was just kind of 2 hops from the first for the first node. And then the same if it was record 57, I would go to the left because 57 is less than 90. 57 is more than 40, so I go to the right, and then I can see it doesn't exist where it should, but I didn't have to do a whole table scan to find out that 57 doesn't exist. It was just 2 hops to get there. Now I could also do ranges this way. If I wanted to find whatever it is that I'm looking for, I want it to be in between 41 and 137. I really only have to go one way. I only have to go to the less than on this. So I go is I'm looking for 41 to start out with. Is 41 less than 90? Yes, so it goes to the left. And then is 41 greater or less than 40? Well, it's greater, so I go down here, and it's going to find where the 41 should be, and then it's just going to start grabbing things along that way because they're in numerical order till it hits the 137 or 135 in this case. So you can see how I can use a B tree to find things really quickly. I think I'm going to stop here again, just again to make the downloads a little faster. And so this is the end of part 2, and then you need to continue on with part 3.